So, last class we are discussing about the frequency domain representation of LQR control systems. So, when we are discussing this one, last class we just recall that our basic Riccati equation, algebraic Riccati equation, which is referred to equation number 3 in our earlier lectures, and that algebraic Riccati equation we added Ps term and subtracted from this one. If you add and subtract, then this is a P s I minus P s A P. So, it is a cancelled that one. Now, this is P A minus P A and this is minus that this is a, you see this one S 1 minus P A. So, that will be minus, here should be A transpose, because our basic equation is A transpose, here is A transpose, agree. Then P B R inverse B transpose minus Q, because our Riccati equation is A transpose P plus P A minus P B R inverse B transpose minus Q. So, both sides I multiplied by minus, it does not matter. So, you got it this one. So, now what we did it this one. So, this will be our transpose, agree. Then pre-multiplied at both pre-multiplied and post-multiplied by the factor this one, and this should be A transpose, agree. Both sides I am pre-multiplied by and post-multiplied by this one. If I pre-multiplied by B transpose minus S I minus A transpose whole inverse, then you have, it is a transpose, agree, and post multiplied by that one both sides. So, here also will be A transpose. So, after multiplying by both sides by P transpose, we got it this expression. So, if you see this expression P transpose this S I minus A transpose this S I minus this, and this is post multiplied by this. So, this quantity and this quantity will be identity matrix. So, P B. So, here only the correction is there A transpose. Then it is a this term you see S I minus A, S I minus this, if you push it in this side. So, this and this will be our A transpose, this as A transpose. So, this will be identity matrix. So, B transpose P multiplied by S I minus A whole inverse B. So, B transpose P S I minus A whole inverse B. Then we have a this term, you see both side I am multiplying by this one. So, this term as it is pre multiplied by this, post multiplied by this. So, here will be a transpose is there and post is this one. This is the left hand side, and right hand side, since we have multiplied by Q pre multiplied by this one, post multiplied by this one. So, this transpose is missing. So, this is that. Now, what we did it from equation 7, we know that our controller gain is nothing but a R inverse B transpose P, agree. So, that if we pre multiplied by R, so K R is B transpose P. So, in this equation, whenever we are getting B transpose P, we will replace by R K. If you replace by this one, the right hand side of this equation, that B transpose S I minus this is transpose here Q S I minus this, and right left hand side of this one P B is replaced by what is called by K transpose R. Actually K transpose R transpose, since R is a symmetric matrix. So, R transpose is equal to R. So, this will be a this one, and for P B I am writing is K transpose R, K transpose R. Then B transpose P I am replacing by R K. So, this is S I minus this. So, this will be a transpose that one, agree. So, that because this is the transpose here. So, if you do this one, then after that we proceed like this way. So, last class we have come up to this point, then we proceed like this way. So, see the left hand side what we can write it, this portion what we are writing next. So, the left hand side we can write B transpose, I am denoting by this one, this by phi s, that S I minus A whole inverse is phi s. Okay. So, then I can write it B transpose then phi minus S whole transpose. See this one, S is replaced by minus S. So, it will be a phi minus S, then whole transpose in place of this is our phi S, then if you take the whole transpose, that will be S I minus A transpose, then your K transpose R, then K transpose R. The next term is R K as it is, you see R K as it is. So, this term I will replace by phi S. So, this will be R K as it is, then I am replacing this is phi S, that means S I minus A whole inverse is a phi S into B. So, this quantity and this quantity is the left hand side. Here you see I have just written this part, but this parts also left it in the right hand side. So, that I have just missed it here. So, I will write it, this is B transpose, then S I minus A transpose whole inverse, then P B, P B is what? K transpose R, K transpose R, that P B. This is the left hand side, we have a this term plus this term, and this term is replaced by this one replacing P B, and this term is replacing by this one, and this also there B transpose, this as it is, P B is now replaced by K transpose R, then we have a R inverse, then B transpose P is a R K into this term, Okay. So, this is S I minus A whole inverse. So, now the third term is coming here, if you see it is a B transpose phi minus S transpose, then K transpose, then your K transpose K transpose R K, K transpose, you see this is as it is, this identity matrix, this is identity matrix. So, K transpose R K, K transpose R K plus into phi K, phi S, agree, plus. So, this we have written it this, then so that this plus this. So, this we can write it to this. So, this we can, if you factorize that one, you will get it plus R K, from where it is coming R K. So, A transpose, our basic equation A transpose B, P B R inverse B transpose, R inverse B transpose P plus that one E 2 plus Q. So, I just both side I added R here, and right hand side also I, in the right hand side of the equation 7 also I added R. So, this agree. So, this adding the, this is the 7 equation, I add R here and R, capital R is at both sides. So, it will not change the expression. So, I have written the left hand side is this one and right hand side is this plus R. So, this is our basic equation of the left hand side. So, this can be factorized like this way, I plus K phi minus S B whole transpose R into I plus K phi S, agree, phi S into B, K phi S minus phi S B whole transpose R this. So, this can be factorized like this way, you just expand this one, you will get it this one. So, if you just tell you briefly, we have started from the Riccati equation, algebraic Riccati equation, then both side I have added that in the not that algebraic Riccati equation, I added P s term and subtracted Ps term. Then after that both side I multiplied by a this expression, the pre multiplied by B transpose minus S I A transpose inverse and post multiplied by this. After multiplying both side pre multiply post multiply and plus R is added left hand side and right hand side. Then ultimately we got left hand side equation is this one and the right hand side of this one we got it that one, this one. Agree? So, now see this one from equation this I can write it left hand side I k phi s plus b whole transpose r plus I plus k phi s b. This is the left hand side is equal to right hand side. Right hand side what we got it? We got it B transpose phi minus S transpose Q phi of S plus R. So, let us call this is equation number 8. Now, look at this one, Q is a positive semi definite matrix, Q is positive semi definite and this quantity will be always positive non negative number for any value of frequency. Okay. So, I can write it this and this equation is called that whole equation, this equation is called the Kalman return difference equation or identity. So, this equation since q is greater than equal to 0 means positive definite means this quantity for any frequency if you shift from 0 to infinity that quantity will be non negative number. So, I can write it this quantity is always greater than equal to than capital R. So, this is the algebraic from algebraic Riccati equation we got this expression and algebraic Riccati equation we need it to solve the what is called gain of the controller to get gain of the controller because we need the value of p and p is the solution of algebraic Riccati equation. So, after getting this one we will see we will now define the gain margin and phase margin of the LQR control systems. Okay. So, we can write it this one that equation 8 this equation 8 from equation 8 using S is equal to in frequency domain S is equal to j omega in 8 we have now I plus k phi S is replaced by j omega. So, it is with j omega then B whole transpose agree wherever the earlier expression 8 equation number 8 S is there S is replaced by j omega this into R plus I plus k phi j omega B this is equal to B transpose agree is equal to B transpose phi minus j omega transpose k transpose then this equal to not k it is a q then you have a this phi j omega into B plus R. So, this is equation number 9 that you see this equation I have written it here putting the value of S is equal to j omega in frequency domain. So, what is the Kalman return difference equation, differential equation. Okay. So, this just I place the S is equal to j omega. So, from 9 putting that reason that since Q is the positive definite matrix, positive semi definite matrix, for any value of frequency from 0 to infinity, if you sweep, that this whole expression will be greater than equal to 0, mean non negative number, because it is pre multiplied and post multiplied by a matrix with its transpose. Agree? If you consider this is a matrix of M Q M transpose, and since Q is a positive definite matrix, whole matrix after transformation it will be a positive semi definite matrix. That means, this is a non negative number. So, from 9 we can write it that I plus k phi j omega minus j omega b whole transpose r is equal pi k phi j omega b, this bracket is greater than equal to r. So, let us call this is equation number 10, and this expression is valid for whether it is a multi input system or single input systems. This expression is valid for all cases. So, now consider this situation, special case, consider a special case. Special case that R is equal to, we consider R is a weightage in the input vector. So, this dimension is m cross m, and this is rho, which is this quantity is any positive number, this equal to I into m. So, we have considered R is diagonal matrix of each diagonal element is rho which is greater than 0. So, from this 10 now we can write it, from 10 we can write it, I plus k phi minus j omega b whole transpose into, because R is replaced by rho I, okay, rho is will be there and right hand side rho will be there, it will be cancelled. So, it will be I k phi j omega b, it will be actually rho into I, R is replaced by rho into I. So, right hand side also rho into I. So, rho cancel. So, it will be a simply identity matrix of dimension m cross n. So, this equation we have observed of this one, and if you see we have discussed earlier, this quantity is nothing but our loop gain. If you recollect our previous formulation, that what we last class we have discussed, see this one, it is nothing but a loop gain, that this whole thing is nothing but a loop gain of the systems. Okay. This G, if you consider the GS, this is HS, GS, HS is the loop gain. So, it is this thing is nothing but a K. So, K into a SI minus A inverse whole inverse, which is I denoted phi of S into B is the loop gain of this one. So, if it is a phi S, this will be nothing but the whole thing will be G L minus J omega L, this whole quantity and its transpose. So, this will be a phi L j omega, S is replaced by j omega and it is a minus sign. So, this that means, we have J L transpose into J L loop gain, this is greater than equal to identity matrix. So, this is nothing but a loop gain or loop transfunctions. So, we can write it now, this I plus G L j omega minus whole transpose into I plus G L j omega is greater than equal to identity matrix. Okay. So, this is the expression we got it for LQR system in frequency domain we got it that 1 plus G s and then you take the conjugate transpose of this one multiplied by this will be always greater than equal to 1. Let us call this equation is the important equation, is representation is very significant. We will see later than this equation number 11. So, from 11 we can write it now, from this one we can write, let us consider a special case, means consider it is a single input single output system. Okay. This is a single input single output systems, though output will not come into the picture in throughout this one, it is our single input system, let us call. That means, our R is equal to 1 and in this case this dimension will be 1 cross 1. So, I can write it now 1 plus G L j omega whole transpose, agree, whole transpose into 1 plus G L j omega, this is greater than equal to 1. Agree? Since this is a single input case, this is the ratio of two polynomials G L, you will get it. Ultimately, if you take the absolute value of that one, what is the absolute value of this one and what is the absolute value of this one, both absolute value will be same. So, I can write it 1 plus G L j omega absolute value square is greater than equal to 1. Again, if this quantity square is greater than or equal to 1, that means absolute value of 1 plus G L j omega must be greater than equal to 1. Okay. So, this is the on ultimately you know the expression for G L loop transfer functions, and our loop transfer function we can write it mod of 1 plus k S I or in frequency domain S, that means j omega, then A whole inverse B mod is greater than equal to 1. Then what is its representation of that one? And it is nothing but a loop transfer function of that is G L j omega. So, let us see is representation in polar plot form. So, I am just plotting in this real of G L j omega part, and here is I am y coordinate is imaginary of G L j omega I am plotting, agree, and this is the our origin and this is the point which is minus 1 plus j 0 point. So, now I draw a circle of unit radius with a center is minus 1 comma j 0, then we have a this one and this radius is 1. I have drawn a circle. Then what is this condition we are getting basically from LQR design problem? We have to find out the controller log, controller gain k is R inverse B transpose P. P is the solution of Riccati equation, algebraic Riccati equation. That Riccati equation we have manipulated, ultimately we got a condition like this way. So, if it is if we now plot it, that what is called Nyquist plot of G L j omega, let us call G L j omega, any let us call this is some plot is there G omega, this is minus. So, what is the distance from this point to any point on the polar plot of G? Polar plot of G is nothing but 1 plus this is minus 1. So, this is 1 and this distance is mod of j omega what is called G j omega this. So, this distance plus this distance will be 1 plus g L j omega values, agree. So, that one. So, this is nothing but a 1 plus g L g j omega. Similarly, here that if you plot it, that what is called our loop transfer function Nyquist plot, it must not cross, it will not cross that unit circle, and that unit circle is I am just representing by shaded. And this is the plot for G L j omega, polar plot of G of j omega, and any point on this curve, that means this indicates that as omega is increasing, it is approaching to the 0, because it is a what is called real transfer function, in the sense that it is a low pass plant of this one. So, this will approach to the 0 of this one as omega tends to 0, this one. And you see what is this from here to here, this quantity is 1 plus G L j omega mod of this one. This is mod of this one is less than that, this is nothing but 1 plus G L this is less than unit circle, this condition. In order to satisfy this condition, this curve, then G L j omega, that means loop transfer function of the system when we have used LQR controller, that should not cross the what is called unit circle. In the other words, it will not enter to the shaded portions by anywhere, agree this one. So, look at this expression that our it does not cross the real axis, this one. So, what is our it cross the what is our gain margin of this one? Our gain margin of this one is infinity. You can, what is the present gain is there, from there you can, this is the at present gain what is there, this is the locus of that one, agree, and this is the polar plot of that loop transfer function based on, I repeat that this loop transfer function is formed based on the LQR controller design, because K is involved in this one, the loop transfer function, it will never cross the shaded region. So, our gain we can add from the present gain, we can increase the gain up to infinity. So, you can say whatever the gain present gain is there, we found out by solving the what is called LQR problem, and what is the present gain we got it, and that gain has a, you can change the gain up to by a factor of infinity. That means, you can increase the gain up to infinity, still the system will be stable one. Now, this is the present gain we can increase, from the present gain what factor we can reduce it, so that the system still maintain its stability. Now, you see this point, if it is a 1, this point is minus 2 comma j 0, this point, agree, this point is minus 2, this one. So, this gain whatever gain present gain is there, agree, at the worst situation it can that loop transfer function can touch this one. So, we can reduce the gain by a factor of half, so that it will touch the minus 1 point. When you are increasing and decreasing the gain of the present gain of this one, phase angle will not change, will not alter anything, only it will change its magnitude at a particular frequency, different frequencies magnitude only will change. Suppose this frequency, at this frequency, let us call this is frequency omega is equal to 4. This frequency, what is the magnitude? This is the magnitude of this one. What is the angle associated of this one? This. So, what is the present gain is there? You increase the gain twice. So, its magnitude only increased by twice, but phase angle will be remain same. Okay. So, if some polar plot of loop transformation, if it is touching here, but it is not entering here, it is just touching, it cannot enter because it is based on the LQR design problem, it cannot enter this one. Then after that we can decrease the present gain by a factor half. So, that this present loop transformation Nyquist plot will just touch the -1 point, till then the system is stable. So, we can say that our gain margin of the LQR design controller based control system, we can increase the gain up to infinity and decrease the gain at least that half. Okay. So, our gain margin you see from infinity to half. What is the present gain is there? Let us call present gain what we got it, the present gain of this system we got it, let us call 5. So, you increase the gain 5 up to infinity by factor of infinity. By if you want to decrease the gain due to some reason the gain is decreasing, if you decrease the gain by a factor of this half, I am telling if the gain is reduced by a factor half, then I can give you guarantee the system will remain stable, it will not unstable, but below this one has to further investigate, but this is the range of gain margin. So, I just write it this that one, the gain, just if you summarize this, the gain from the present gain, one increase the gain up to infinity 1 can decrease the gain by a factor half. So, our gain margin is minus infinity to by half this one. So, so equation, now you see this is our equation number. What is the equation number? Anyway, so let us call this equation number, you give it 12. Okay, we have given up to 11 we have given. So, this equation number we have given is 12. So, from 12 one can see that what is called this conclusion is made from equation number 12. So, before that we study the gain margin, those I will just gain margin we have done it, phase margin we have to do it, just how to study the stability of a control system based on Nyquist stability criteria, that I will just briefly discuss here. So, that it will be easy for you to understand this one. So, let us call we have a closed loop system like this way. So, our GS, agree, our GS is this one and our HS is a feedback path transformation is that one, and this is our CS or YS, people are also writing YS, this is our RS. So, our loop transformation is what? You see loop transformation is nothing but a from here to you just complete the loop, and what is the transformation you get it, that is the loop H of S. So, if you see how to study the stability of this system by using what is called Nyquist stability criteria, the first thing is we have to see the what is the our Nyquist path. Our Nyquist path is the whole write up of the S plane, agree, whole write up of the S plane, and this is our real S, this is our imaginary S. Agree? And if you have any pole at the origin, then you bend this curve like this way, either left hand side, right hand side or left hand side, bend it, so that it should not be value of the function, that trans function should not be infinite, because you see one, if we s divided by s plus a numerator divided by s into s plus b, when s tends to 0, s is 0, this becomes infinite, this one. So, this infinite, but we just make it limit in this one, there is a small, this quantity is the epsilon e to the power of j theta. When we will just put limiting value and evaluate the function value along the Nyquist path, and this is the Nyquist path. Agree? This is the Nyquist path. Then omega is equal to 0, omega is equal to 0, omega is equal to, we will just write epsilon theta of this one, very small value, we just go on this one. So, you can write it omega plus, omega is equal to 0 plus, this is the omega is equal to 0 minus. So, that arc is a epsilon e to the power j omega, you going like this way, and this is the omega is equal to infinity. Okay? And this is omega is equal to minus infinity. So, this is r e to the power of j theta, and r is tends to infinity, this one. So, we will find out the loop transform function Nyquist plot, loop transform Nyquist plot, while we move along this Nyquist path from 0 to omega, 0 to infinity, we sweep. Once you know from the Nyquist plot of loop transform function from 0 to infinity, then minus infinity 0 is the mirror image of that polar plot, we can do it this one. So, our Nyquist stability criteria says that let us call for the given system our Nyquist stability and what is called polar plot of that one is like this way, just touching this one, and this is the minus 1 j 0 point. Agree? And it cuts is here, and if you see this one with a unit circle, if you draw a circle of this one, agree, and this is the gain crossover frequency, this is the gain crossover frequency omega g c, and this is the phase crossover frequency, phase crossover frequency. So, our gain margin, if it cuts here, then reciprocal of this distance will be our gain margin. That means, we can increase the gain by a factor, what is called reciprocal of that one. What is, suppose this is A, we increase the gain by factor 1 by A. Okay? So, it is a gain margin of this one, and if you assume that no poles, open loop poles are right up of the S plane, then only we can say gain can be increased this one. So, in general is Z is equal to that P plus N. Okay? And what is this, the phase gain crossover frequency, we will get it what is called phase margin. This is our magnitude of the polar plot, and this is the phase angle. So, we can introduce additional phase this much before the system becomes unstable. So, we have this criteria, we have to check it. This is the, you can say, number of poles, number of which poles, open loop poles, rather loop transformation poles, agree, in the right half of the S plane. This is n, and this n is the number of encirclement of the point of the critical point minus 1 j 0 number of n circle of the critical point by the polar plot of the loop functions. I mean, suppose there is no poles in the right half of the S plane, open loop transformation poles, there is no poles, that is P is 0. Then n is n, if n does not encircle minus 1 point, then P is 0, n also 0, it does not encircle minus 1 point, is encircle 0. So, P 0, n 0, so Z is 0, Z 0 means it the system, there is no closed loop poles in the right half of the S plane. That figure Z number figure, what we will get is Z is equal to, let us call it, we got it 0, that means no closed loop poles of the system lies in the right half of the S plane, that means system is stable. Suppose there may be system, open loop system is a unstable, loop transformation is an unstable one, and we have seen there is a two poles are in the right half of the S plane of the loop transformation or open loop poles, the two poles on the right half of the. So, P value is 2. So, in order to become the system 2, that n must be 2. So, that this, if the encirclement is clockwise, if the polar plot encircles the minus 1 point in clockwise, then its sign will be considered as a positive. If it is enclose the minus 1 point in anticlockwise, that its sign will be considered negative. That means, this if the polar plot encircle the minus 1 point clockwise direction twice, then we will write 2 plus 2. If it encircle the minus 1 point counterclockwise twice, then we will write it that 2 minus 2, sign is minus will be considered. So, in this way we can study the stability of the closed loop system, even this system is a non minimum phase system, that means poles in the right half of the S planes, if it is there open loop poles, that we can study the stability of this one. Now, so, now we will see this one, that what is called phase margin. So, what is the gain margin? What we have seen, if you design a controller based on the LQR controller, that controller has a gain margin up to infinity, okay, and that what is the present gain is there of the LQR controller design, present gain is there, that gain you can reduce by a factor half. So, gain margin varies from infinity to half of factor. I am talking about the factor, the what is the present gain is there, that gain you can multiply it by a infinity, very large number of that factor, that means infinity, or you can multiply that present gain of the LQR controller by a factor half before it becomes unstable. So, it is a very robust, even though controller parameter change, it guarantees the system is stable, this one. So, let us see is phase margin. So, let us plot it this one. So, minus 1 j 0 this point. So, I am just plotting this. So, this is 1, then this is I am just plotting real of G L j omega, this is imaginary of G L j omega. Okay. Then another circle I am drawing it with this one, center of 1, I am drawing the center this is also no, it is okay. Just once again I will draw it that one phase margin. So, this is a minus 1 j 0 and in this I am real of g l j omega, in this an imaginary of g l j omega. Okay. I am just drawing a circle with a center this of 1. Okay. And this is with a center 0 with a radius 1, I am drawing another circle. This is also 1 and this is also 1, let us call agree 1. Now, this is minus 2, this one is minus 2. Now, see, according to the LQR design problem, we have shown it that if your the loop transfer function plot is like this way, it will never enter to the region of that one shaded region, that is by condition we got it. Agree? So, it may touch it here, this thing purport it may touch it, but it will never enter to this one, it may touch this one. So, if we just add this point and add this point, you see this radius is though it is not done properly, but this radius is 1, this also radius is 1, agree, and if you just add with draw a line from here to this is also 1, this is also 1. From this triangle if you see this is 1, because with this center or with the origin is the center, we have drawn a circle of radius 1. So, when the two circles are crossed this point, let us call this is P 1 point and this is the P 2 point. Agree? Then P 1 point from this point to this point, this because we have drawn a circle with a unit radius, center is minus 1 j 0. So, this are all is same length. So, this value will be 60 degree. Similarly, this length and this length 1 1 1. So, this will be a 60 degree. So, one can come to conclusion, since this curve will not enter to this what is called in the shaded region, it can touch, because why it can touch, you see 1 plus k or 1 plus g l j omega mod will be greater than equal to 1, because it is when equal to 1 it will touch, this is the condition, this one. So, if it since it cannot enter into this point with the present gain of the controller. So, maximum or at least the phase angle will be what 60, because it can touch it here, this curve can touch it here. Then what is this one? If it is this, then this is the phase angle of this one. Suppose it is this one, phase angle of this one is that, agree, and this will be 60. That means, additional 60 degree phase can be introduced into the system when the controller is designed what is called based on LQR, at least 60. It can you can introduce, because you can introduce further more than 60 degree. So, our phase margin is greater than equal to 60. So, it will be a 60 and it will be more than 60, because it can touch only, it cannot enter in this one. If you can enter here, then it violates our condition which we derive from the algebraic equation, and the algebraic equation is coming from the design of the controller LQR controller. So, our phase margin will be greater than equal to 60 degree, at least 60, it may be more than, say it will be more than 60. So, this is the phase margin of this one. So, in your short, if you design the LQR controller, it ensures that our gain margin is infinity and half. That means, what does it mean? We have designed the controller K based on LQR, and that gain can be increased by a factor. I say increase by a factor up to infinity. That means, gain, whatever the gain is, gain can go up to infinity, and similarly then system will remain stable, and similarly the gain can be reduced by a factor half. What is the present gain is there? Let us call present gain is 10. I can go reduce the gain up to 5. Up to 5 I can tell the system is stable. So, if there is a gain variation is there after designing the controller, then it is the system will stable in this region. That means, it is a robust, more robust, and not only this, it also ensure that it is a good what is phase margin also retained. That means, 60 degree is minimum, it may be more than 60 degree of this, it will be more than 60. So, let us take the, or just if I write it, the since the Nyquist plot, since the Nyquist plot of an optimal regulator must avoid the unit circle shaded region centered at -1 J0. So, our possible points are that we have shown it, our possible points are this one P1 and the P2. This is the two possible points are there. Well, points are P1 and P2, and P1 P2, if you see the P2 is 60 degree. So, 1, that means, it is coordinate is minus half minus j root 3 by 2 this, and this coordinate is minus half plus j root 3 by 2 again this. So, this is the our ultimate conclusion. If you recollect our earlier example, let us see what is our gain margin and phase margin, what we will achieve after implementing through what is called LQR controller. If you recollect our earlier example, that is x is equal to 0, 1, minus 2, 2 x, then b is 0, 1, that is b, and our performing index is half 0 to infinity x 1 square plus x 2 square plus twice u square of this dt, and you have to put in proper what is called expression format, then you apply the LQR controller, that we have solved it earlier. You just recall the earlier example, and our problem is to design a controller u is equal to minus x t, where x is the controller gain based on the LQR design technique, and we got the controller gain. If you recollect, we got the controller gain 0.121 and 4.178 the controller gain, if you recollect then. And what is our loop transform? Once we get the controller gain, how you got it? We have solved the Riccati equation, then we got it k is equal to R inverse B transpose P. P you know, B you know, R you know from this expression. So, once I know this one, I can find out GL j omega. GL j omega will be coming if you do this one k S I minus a whole inverse b, this is our what is called GL, and put S is equal to j omega, and if you put it this one this GLS, I am getting it 0.121 plus 4.178 S divided by S square minus twice S plus 2. If you do this operation, you will get it that one. So, you plot the Nyquist plot of that one. If you do the Nyquist plot of this one, what you will get it, you will see this one. I am just how to plot the Nyquist plot, you just put it, you see this figure Nyquist plot. This is the, in this axis real of GL j omega, and in this axis the imaginary of GL j omega, plot it. Then it will see, it will start from here as omega is equal to 0, it is here, and omega is increasing, this GL plot, this is the GL j omega plot, this is the omega is equal to 0 plus, and this is the origin 0 0, and this is the omega is equal to infinity, plus this, you got it this one. Now, see this one, our 2 point minus 2 points is here, this one, it is outside this, it is not entering to this one, the Nyquist plot of that one, again is not entering to this one. Our, if you draw a circle with a minus 1 circle of that one, you will not enter this one minus 1 of that one. Okay. So, you can find out it is the gain margin is infinity, you see it will not cut here, as you increase the gain of this one, it will be infinity the gain margin. From the present gain, if you decrease the gain by factor half, still then this will be a stable of this one. Okay. So, at least half, it may be less than half also, it will be stable this one. Then if you see the Bode plot of this one, Bode plot of GL j omega, this is the thing, and from the Bode plot of this one, the gain margin, the phase margin you see 60 degree, 60 point, you are getting the phase margin is 60.7 degree, and we, according to theorem, it is told at least 60 degree, that phase margin is phase margin PM is 60 degree, greater than equal to 60 degree, we are getting 60.3, and our phase margin, and gain margin is, you see our gain margin is equal to minus 6.24 dB, that you got it that one. Okay. That you can easily find out what factor is there, you can reduce the present gain of the controller, and it occurs at omega is equal to 1.43 rad per second. Okay. So, this very verified our what is called statement we made it in LQR control, phase margin is greater than equal to 60, and the gain margin is gain is very infinity and by a factor of half also. We will stop it here today.